Welcome to Cambridge Chemistry channel with Sarvat Ahmed. Be sure to like the video and subscribe. It really helps the channel to grow. In this video, I will be explaining enthalpy change of hydration of an ionic solid. It is involved, and that what do you mean by enthalpy change, and we represent enthalpy change of enthalpy change. This is the sign of enthalpy change of solution and hydration under standard conditions in their standard states. This is for hydration, enthalpy change of hydration, and this is how to represent enthalpy change of solution. Enthalpy change of solution. Ionic solid is dissociated in water, and this process may be exothermic or endothermic. And enthalpy change of hydration of an ionic, it is involved when an ionic solid dissolves in excess of water. And enthalpy change of hydration can be defined like that: standard enthalpy change of an ionic solid is the enthalpy change measured under standard conditions when 1 mole of the solid, 1 mole of the ionic solid is dissolved in excess of water to form infinitely dilute solution. This is the definition of the enthalpy change of hydration under standard conditions in their standard states. For example, like calcium ions in gaseous states when dissolved to form calcium aqueous ions, and delta H hydration is equal to minus 1650 kilojoule mole inverse 1. So this is the energy released during the hydration of this gaseous ion. And similarly, chloride ions in gaseous state when dissolved in excess of water to form chloride ions, and delta H hydration of is equal to minus 364 kilojoule mole inverse 1. So these equations indicates that this is more exothermic and this is less exothermic. Why? The dissolving of calcium ions in water is more exothermic than chloride ion, less exothermic. So we know that more exothermic for ions with the same charge but smaller ionic radius. For example, delta H hydration of lithium is more exothermic than delta H hydration for sodium ion. So this is very important point to always keep it in mind. More exothermic for ions with the same charge but smaller ionic radii. For example, delta H hydration is more exothermic for lithium ion than for sodium ion. So in this way, in other words, we can say that down the group delta H hydration is less exothermic. So note down. In other words, down the group delta H hydration down the group 1 and 2. Delta H hydration is less exothermic. If less exothermic, so more energy. And another point is, which is very important, that more exothermic for ions with the same radius with the same radius sorry but a larger charge. For example, delta H hydration is more exothermic for magnesium ion than for lithium ion. So we can say that across the period like sodium ion, magnesium ion, aluminium ion. Delta H hydration become more exothermic. More exothermic. Next is enthalpy change of solution. Delta H enthalpy change of solution is the energy when 1 mole of an ionic solid dissolved in excess of water to form a very dilute solution. It can be exothermic or endothermic. For example, magnesium chloride solid plus aqueous to form magnesium true positive aqueous ion plus true Cl aqueous ion, two chloride ions. And delta H solution for this reaction is, according to data booklet, that is equal to minus 55 kilojoule mole inverse 1. So there is another example, sodium chloride in solid state when dissolved in water to form sodium ion and chloride ion. And delta H solution for this reaction is equal to plus 3.9 kilojoule mole inverse 1. So as you have seen that magnesium chloride, dissolving of magnesium chloride in water is exothermic, while dissolving of sodium chloride is endothermic. So I will be explaining this on the basis of attraction between the ions. So this is the attraction between the sodium chloride ion is the ion dipole attraction, which is formed when ionic solid dissolves in water like this. This is the ionic lattice. This is ionic lattice. When it dissolves in water, the force of attraction is going to develop between the ionic positive ion of the ionic lattice with water. So water has dipole when dissolved in water. So this is like this. Positive, partial negative, and this is dipole developed on water molecules, and this will be water molecule. Like positive ion is surrounded by water molecule. Positive ions surrounded by water molecules, like positive ions surrounded by water molecules in such a way that it is directed towards negative end of the water molecule. All around. So this is for positive and this is negative ion. So in this way, ion dipole force of attractions are going to develop in between the water molecule and the ionic lattice. And this is the force of attraction when lattice of the ions when dissolved in excess of water, or it is surrounded water molecules like this, that positive surrounded uh, positive is directed towards negative ion of the water molecules, and negative ion of lattice solid is directed towards the positive end of the water molecules. Dissolve, so dissociation of 1 mole of ionic solid into gaseous ions. involves following process. Number one, this involves energy which is equal to the enthalpy change of lattice energy of the solid but with the reverse sign. And this step is endothermic. Number two, conversion of gaseous ions into aqueous ions. This is for individual because of this is for individual cations and anions. Sorry, this is for individual cations and anions. And it is exothermic because of attraction between the ions and polar water molecules. Polar water molecules mean that oxygen carrying partial negative charge and hydrogen carrying partial positive charge. So the covalent molecules which have two poles, positive, partial positive and partial negative, are known as polar molecule. We have discussed in AS level polar and non-polar molecules. Now Hess law, we use another color. Hess law is applied to calculate delta H solution of an ionic solid like this triangle cycle. Gaseous ions so gaseous ions into aqueous ion is exothermic. So this is zero ion and Ionic solid in aqueous solution. This is also exothermic. This is delta H solution, and this is delta H hydration. And this is delta H lattice energy. So this cycle is gaseous sign to ionic solid and then in aqueous. And delta H hydration of cations and anions plus anions. So we can solve by using this delta H lattice energy plus delta H solution is equal to delta H hydration. We can draw this by using Born-Haber. We can calculate this by drawing Born-Haber cycle like this. Sodium chloride. This is how to draw Born-Haber cycle. Sodium chloride solid is formed sodium gaseous sign plus chloride gaseous, gaseous sign. There is ionic solid sodium chloride is formed. Delta H hydration. Sodium is equal to minus 390 kilojoule mole inverse 1 and changes into sodium aqueous sign. State symbols are very important to note down, and this is delta H hydration of anion chloride, and this is equal to delta H is equal to minus 380 kilojoule mole inverse 1. And now changes into sodium aquosign plus chloride aquosign. Now sodium chloride solid state formed from gaseous sign. So sodium chloride, when dissolved in water, it formed sodium aquosign. This is direct method, and this is delta H solution, and this is gaseous to form ionic solid. This is indirect route. In direct routes, you know that 1 mole of ionic solid dissolves in excess of water to form an infinitely dilute solution, sodium aquosign and chloride aquosign. And in indirect route, this involves 1 mole of ionic solid into 1 mole of ionic solid is formed from 1 mole of sodium gaseous and 1 mole of chloride gaseous sign. So this is how sodium chloride is formed. So this is equal to lattice energy, and this is equal to delta H solution, enthalpy change of solution. And this is how ionic solid is formed. This is equal to delta H lattice energy, which is negative, and delta H solution is positive in this case. And sodium chloride, sodium and chloride ion in gaseous form, when dissolved in water, it changes into sodium aqueous and chloride aqueous ion, and this is equal to delta H hydration. And this is delta H hydration of cations, which is exothermic, and this is delta H of delta H hydration of chloride ion, which is also exothermic. I will be writing this explanation of root consists of two roots: direct root. In direct root, 1 mole of ionic solid dissolves in excess of water to form an infinitely dilute solution. And this is equal to delta H solution, which is endothermic. And indirect route involves 1 mole of this involves 1 mole of ionic solid is formed from 1 mole of from gaseous anions and cations. This is exothermic and equal to enthalpy change of lattice energy. Now gaseous sodium ion and chloride ion now dissolves in excess of water to form aqueous ions. This is equal to the delta H hydration, and which is delta H hydration is equal to sum of delta H hydration is equal to delta H plus delta H sodium ion and delta H of anion or chloride ions. And by applying Hess law, it can be calculated by using delta H delta H solution is equal to sodium chloride is equal to minus delta H lattice energy plus delta H hydration sodium ion plus delta H hydration of chloride ion. So by using data booklet, we know the values. Delta H solution is equal to, this is delta H lattice energy of sodium chloride when it is formed from sodium gaseous and chloride gaseous ion, and this is delta H hydration of sodium ion and this is delta H hydration of chloride ion. And the delta H solution of sodium chloride is equal to Ma plus 5 kilojoule mole inverse 1. So this is the general formula. I have to write down general formula of delta H solution is equal to delta H hydration cations plus delta H hydration of anions minus delta H lattice energy. So this is the general formula to calculate delta H solution or delta H hydration of cations or anions and delta H lattice energy like this.